Well, I was going through the book and I got to number 5 here in section 11.2. I thought maybe we should talk about it a little bit. I meant to find a formula for the nth partial sum of this series, and looking at that, I think that might be difficult. I mean, this is not the geometric series that I've been looking at in the previous examples. So I look at this and I see, oh, this is a rational function, and one of the tools that I know to deal with rational functions is the method of partial fractions, which is a way of splitting apart a single rational function into a sum of two rational functions. So let me write this out. By finding A and B in R, the real numbers, such that, let's see, A over n plus 1, okay, the first factor of the denominator, plus B over n plus 2 is the summand here, the thing in the sum. A word a lot like integrand, the thing inside. Okay, now that equation, for all positive values of n, when the denominator is not 0, that just says that A times n plus 2 plus B times n plus 1 is, no, the idea is to multiply all of the terms with the denominator there, so 1. And that is equivalent to saying, now we'll match up the coefficients of n on the left, that is A, and B, that's the coefficients of n to the first power over here, is equal to 0, matching up the coefficients of n to the first power over here. N doesn't appear over there. And matching up the constants, the things that don't have n's attached to them, 2a plus b is equal to 1. Okay. Now, I can rearrange some of these equations, right? So this first guy, I'll say that b is negative a, and I'll use that in the second thing here, so I'll say 2a minus, and I'll replace b with negative a here, so this. Okay, so that just says that a is equal to 1. B is equal to something, and a is equal here, that this just says that a is equal to 1, and then b has to be negative 1. Okay. Well, then the nth partial sum over here, or let's go with capital Nth partial sum. I noticed that your book likes to use k for the index and lowercase n for the nth partial sum, but it doesn't really matter. I could use a picture of a cupcake to denote my cupcaketh partial sum. Yeah, any old symbol will be fine. Okay. The nth partial sum of sum n equals 1 to infinity of 1 over n plus 1 times n plus 2, which is the sum from n equals 1 to infinity, 1 over n plus 1. Let's see, it says a, because a was 1, minus b over something, n plus 2, is Sn is, let's see, so the first term here, okay, let's write out the first term. The first term is within is 1, that's 1/2 minus 1/3, right, because n plus 2. The next term is 1, okay, so the n equals 2 term is 1/3, and then I subtract from that 1/4, and I notice that the 1/3 and the 1/3 vanish. The next term we'll have n is 3 for that third term. That'll give me a 1 over 3 plus 1 is 4, minus 1 over 3 plus 2 is 5, and I see that these vanish, And what I'll do then is say plus dot 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 dot. And I see that everything's going to vanish except for that last term, right? So every time I write a new term, the first part of that new term cancels the second part of the previous new term. So the only thing that's going to survive this process is the first term in the whole partial sum here, 1/2, and the last, which will be minus 1 over n plus 2. Okay. Now, I'm not real fond of writing the slash notation, but I made an exception to that rule here. So I see simply 1/2 minus 1 over n plus 2. That, my friends, goes to 1/2 as n goes to infinity. And interesting. So this kind of thing is called a telescoping sum, by the way. This partial sum, you write it all out. This is big, long expression, but everything in the middle just collapses down. Kind of like an old school telescope would collapse down. You know, the kind of thing a pirate would use.